In AP Chemistry, one of the main things you do with a solution is titrate it. That means if the solution is an acid, you can find out its concentration by reacting it with a known amount, or finding how much base is required to react with it. If you need a lot of base to react with it, you must have a pretty strong acid. That's usually the basis behind a titration. So here's the definition. A solution of accurately known concentration, that's your known stuff, is added gradually to another solution of unknown concentration that you know it's going to react with, preferably at a 1-to-1 ratio, until it's complete. Strong stuff will require a lot of stuff to react. That means concentrated. Dilute stuff will require very little to react, and it's a proportional effect, so you can use basically C1V1 equals C2V2 if they all are nice, completely dissociated systems to do a titration. The equivalence point is the point at which the reaction is complete. There are these wonderful indicators you can add to the solution that as soon as it crosses over a certain pH threshold, the structure of the indicator changes and it becomes hot pink, or it becomes Congo red, or some one of these colors. The indicator is the stuff that you add that will change color at or near that equivalence point. And that's what it looks like in practice. You drip some stuff in. That's called a burette. That is your Erlenmeyer flask. There's your indicator. And that is a squeeze bottle. So you slowly add base to the unknown acid until you get a nice color change, or you can do it by monitoring the pH as well. It zips up rapidly when it hits the equivalence point. You can use it most commonly for the analysis of acid-base reactions, and it's much more convenient when your acid is your unknown, because that's when you'll go from colorless to colored. For example, sulfuric acid can react with sodium hydroxide. And there's your pale pink endpoint, meaning you just started to change color. You did it perfectly. It can also be used for redox reactions that involve either acid or base, and you can get a color change for those as well. Let's do a problem. In a titration experiment, a student finds that it took 23.8 milliliters of a sodium hydroxide solution to neutralize 0.5468 grams of potassium hydrogen phosphate. What is the concentration of the sodium hydroxide solution? Well, let's see. We can figure out how many moles of potassium hydrogen phosphate were required. I mean, it's only half a gram, and 200 grams are a mole, so it's a very small amount of moles, somewhere in the thousandths of a mole. And we do know that we have 0.02348 liters of solution. They want the concentration, so all we need to know is the moles. Now we'll be calculating, right? Moles per liter is concentration. We know liters. We need to know moles of sodium hydroxide. But we can calculate the moles of KHP, is what they call this stuff. And since they react in a 1-to-1 ratio, although that's not given, trust me, they do, that means that the moles of KHP is the moles of sodium hydroxide that it reacted with. Make any sense to you? Let's see. We need blah, 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 blah. Have a look at that if you want. So moles per liter, they want the concentration. There's the concentration. And in fact, that's easy, 0.02348 liters, right? There's 1,000 milliliters in a liter. And we just need moles of sodium hydroxide. That's equivalent to the moles of KHP. How many moles of KHP? Very little, right? 0.55 grams and 200 grams is a mole. We got 0.00268 moles of KHP. That's your top number, moles per liter. This is a 0.1141 molar solution. This should be enough to do some quick titration problems. We have multiple chapters later on devoted to titration, so this will be a quick exposure to it. Hey, that ends the chapter. You can now solve like 100 problems.